So Unit 5, Lesson 8. We got one more unit after this, trigonometry. So you got review on Monday, test Tuesday, but your review day is going to be half and half. We do have to start the next unit. Okay, so what we have here is investigating geometric series with r equals 1/2. So r, remember, that's a common ratio. We are talking about geometric still, infinite geometric. And infinite just means it goes on forever. So David buys a pizza, he eats half the pizza, then half the remaining piece, etc. Okay, continuing this way, it looks like he'll never finish the pizza because there'll always be the half of that piece left. Explain why this practice could not happen. Well, you're going to get to a point where you can't half it anymore. In terms of like realistically. Okay. Represent the situation of the geometric series whose first term is 1/2. So since it says series, I want to make sure I put plus sign. So it's 1/2, then it's going to be plus 1/4 plus 1/8. So I'm going to keep halving it. Plus 1/16 plus and etc. Okay, for this series, determine the values of A and R and a formula for S sub n. So we know that A is 1/2 because that's the first term. We know that R is 1/2 because that's what we're doing to it every time. And if I went ahead and used my series formula of A times R sub n minus 1 all over R minus 1, and then I plugged in the stuff I have, I would have 1/2 times 1/2 to the n minus 1 over over 1/2 minus 1. And with that, I'm just going to kind of skip to where it simplifies to. If you simplify that, it's going to come into 1 minus 1/2 to the n. Okay. If you put that far right, let's just do that right now, put that far right into your y1 and hit second graph, and it'll bring up the table. Okay? Everybody have one? Okay, so it's 1 minus and then hit second graph, and you'll just kind of get these values here. 1 will be 0.5, 2 will be 0.75, 3 is 0.875, 4 is 0.938, 0.969, 0.984, 0.992, 996, 0.998, and then 0.999. So you can kind of just see it just keeps getting closer and closer and closer to 1, but doesn't quite get there. Okay, and it never will. It'll just keep getting more 9s. Okay, we'll talk about what that means in a second. But again, if you're still catching up, we did y1 is this. Okay, and then you hit second graph, and it kicks out your table so you can fill this out faster. Okay, so we're going to plot these next. So mine are going to go away, but hopefully you still have yours. So we're going to plot it, see what that graph looks like. Okay, so at 1, it's 0.5, 2, 0.75. Let's see here, that would be 0.6, 0.75, 3, 0.875. 4, 0.938, 5, 0.96, and this kind of keeps going, just inching up more and more every time. So it kind of looks something like this in terms of a line. Okay, and S1, S2, S3, all these numbers get close to the value of 1. Okay, and this is key for today. This type of relationship is called a convergent graph. Okay, it's converging to a number. It's flattening out at a number. It can't get to it, but it's getting really, really close to it. It would appear that if we add the terms of this series indefinitely, we'll get closer and closer to the value of 1. We say that the sum of the infinite geometric series is 1 because we're going to, if we do it forever, it's get close enough where we can just assume that it gets to 1. So what that means is that this series, if we just keep adding it for the rest of our lives, we're going to get 0.99999999999 all the way through, and we'll just view that as 1. We're saying, okay, it's going to 1. We know that, so we're going to put 1. Okay? So then it says here on G, explain with the reference to why the sum is going to be 1, because eventually the pizza will be gone. For our example, eventually the pizza will be gone. Okay? Okay, and we're going to talk about the other kind here. There's two kinds, convergent and divergent. So we're going to talk about divergent. Okay, so investigation 2. Our R is 2 this time. Consider the infinite geometric series of 2, 4, 8, 16. So for this series, determine your A is 2, your R is 2. Okay, if we do the formula again, we have S of n equals A times R to the n minus 1 all over R minus 1. So we plug in what we have. We have S of n equals 2 times 2 to the n minus 1 all over 2 minus 1. You'll see that 2 minus 1 is just 1, so the bottom essentially just goes away. So this simplifies to just this. You can put that in your calculator again. You can hit second graph. So put this in your Y1, hit second graph, which is table, and you can fill out this table. Start filling it out here too. So we get 2, 6. Okay, give you a second to get that down, then we'll go ahead and plot again, and you'll see the difference. Okay, so let's go ahead and look at it plotted now. Okay, so if I plot it here, we got 1 is 2, so it's going by tens here. So 1 would be right here, 2 would be 6, 3 would be 14, 4 would be 30, 5 would be 62, 7 would be 126, way up here. So you can see it's taking off. So it's not approaching anything, it's taking off. That is a divergent graph or relationship. Divergent does not have a sum to infinity. Okay, keep that in mind for later. Does not have a sum to infinity. So you can't find that geometric sum for that series. So we've seen that R equals 1/2 converges, and we've seen that R equals 2 diverges. Okay, so what we're going to do now is we're going to look and see about the other possibilities and see if we can make an assumption or make the rule of what converges and what diverges. Anybody want to make a guess? guesses? What diverges, what converges, you think? Converges if it's a number between 1 and 0. That's correct, yeah. So what we're going to do is we're going to try all those. So we're going to try a number that is less than -1, between 0 and -1, so here's a fraction, between 0 and 1, fraction, and then greater than 1. So the ones we're going to try, they tell us to try -2, -1/4, and 2/3 and 3. Okay, you could use your table and your calculator for this. You could put, if r is -2, you can put in your calculator not highlighter. You can put -2 to the x in your calculator and then figure out what these are. You can put -1/4 to the x, figure out what those are. 2/3 to the x, figure out what those are, and then 3 to the x, and figure out what those are. And I'll just go ahead and fill it out here as you're doing that as well, and kind of see the relationship. So we know that this is going to be -2, 4, -8, 16, 1024, 104, 8576, and 1.3 times 10 to the 30th. Okay, let's look at -1/4. -1/4, I get -1/4, 1/16, -1/64, 1/256, 9.5 times 10 to the -7, 9.1 times 10 to the -13, 6.2 times 10 to the -61. Okay, then we have 2/3, 4/9, 881 or 27ths, 1681. Then we're going to have 3 times 10 to the -4. Oops, forgot one. We're going to have 0.173. Then we're going to have 10, 3 times 10 to the -4, 2.5 times 10 to the -18. So we kind of see the point here. Well, I'll finish the last one. But kind of see the point. These are really, really small numbers. Okay? This is a really big number. Okay? Because these are scientific notation. I'm adding 30 zeros here. I'm going backwards, so zeros in front of the decimal here and here. Okay? So then come to this one, 3 to the x. So we get 3, we get 9, 27, 81, 59,049, 3.5 times 10 to the 9th, and 5.2 times 10 to the 47th. Whew, a lot of zeros, 47 zeros. Okay. I know it's tedious, but it's kind of showing the example of actually how they do converge, okay, or diverge. Okay, give you a second here if you want to drop those down, if you can even read it. All right. Okay, and we're going to go ahead and go to what does this mean? So, B, complete the following statements based on your results. Okay, the sequence is convergent as it approaches a value of 0. So convergent is the ones that have flattened out. Okay, those are at -1/4 and 2/3. The sequence were divergent for -2 and 3. So along with what Tristan said, if the ones that are between -1 and 1 fractions, okay, those are going to be your convergent. If it's bigger than or less than -1 and bigger than 1, that's going to be your divergent. Now, once you get those understood, this section's super simple because this is the easiest formula you have. So if you can't find the sum of divergent, the only one you have to do work for then is what? The convergent ones. So if it's convergent, then you can actually find the sum of it. If it's divergent, you put D and E. And we'll get to that here in a second. Okay, so one little overview, then we got some examples, and then we're done. Okay, so the formula for the sum of geometric series. So consider, your series here. Here's our original formula there. It can also be written in this way, which is the same, just reversing the minuses. And so what they're going to do is they're just going to go ahead and, provided that it's between -1 and 1, okay, because these numbers will help us get what we're looking for in terms of being convergent, we can use this formula here when they're convergent, or this one here. And it's built off our original. Okay. All right, so going through a little flow chart here could be helpful. Okay, so geometric series in general, we have two types. We have finite, where we use the formulas we've learned yesterday. So we use either this one or this one. Okay, with that just reverses the inside, which is okay. Or if we don't know the term, we use this one. So that's if we have geometric series. It's finite, means it has an ending point. If it's infinite, it goes on forever, we have two options, convergent or divergent. If it's convergent, we can use this formula. Those are when your R is a fraction between -1 and 1. Divergent, we can't find its sum, so it's D and E. It does not exist. The sum for divergent is not possible because it keeps going on so massive that it's essentially infinity, but you can't use an infinity as a number because infinity is not a number, it's a continuous forever. That's the best way to say it, I guess. Okay. Any questions there? Okay, so now the examples now will kind of finish it for us. Okay, so example 1, determine the common ratio and if it's convergent or divergent. Okay, because that'll tell us if it exists or not. So the first thing is we want our A, 1. We want our R is 1/3. Okay, so if my R is 1/3, is that convergent or divergent? Convergent, so I can use the formula. Remember, these three dots mean it goes on forever, so it's an infinite series. So what we're going to do is we're going to do A over 1 minus R. That'll give us our answer. 1 minus 1/3 is 2/3. 1 over 2/3 equals 3/2. So this one's sum, the sum of that series is 3/2. Okay, for B, my A is 1, my R is -5. This is divergent, so the sum does not exist. Okay, the last one of this section here, my A is 2, my R is -1/2. So that one is convergent. So this one was convergent. This one's convergent. So I can use the formula. I can go 2 over 1 minus -1/2. It is minus a minus here, so make sure you make note of that. So that makes it a plus. So 2 over 3/2 gives you 4/3 when you simplify it. All right, and one now of working backwards, the next one. So the next one, the first term of the geometric series is 2, and the sum to infinity is 4. So it gives me the sum, and it gives me the first term. So it gives me A, okay, and the sum to infinity is 4, and A is 2. We want to find R. Okay, so what we need to know is, note that little double circles is the infinity sign. Okay. Well, we know it has to be convergent, so right now you can already know that, okay, it's going to be between -1 and 1. Has to be. Okay, so let's set up our formula. So 4, I'm going off this formula here. Remember, sum to infinity is a over 1 minus r. So I'm going to set that up. So a over 1 minus r. I'm going to solve for r. What I'm going to do is, to get rid of this fraction, I'm going to times 1 minus r to both sides. Okay, that's going to give me 4 minus 4r equals 2. Minus 4, minus 4. Negative 4r equals negative 2. And then divide by negative 4. We forgot our common ratio is 1/2. Okay, if you have something bigger than 1, then you'd know you did it wrong, because you couldn't get anything bigger than 1. Okay, and this one actually is, I don't know, you actually do this in calculus. If you're taking calculus, we do this. It's kind of interesting, I think. You can figure out what fraction makes a repeating decimal without, if you're just given the repeating decimal. Okay, because the repeating decimal goes on forever, right? So we can use that to our advantage. So for example, if we take 0.07 repeating, so it's saying the 7's repeating, right? So it means if I put that into an infinite series, it would look like this. Right? Does that make sense? Because 0.07 plus 0.007 is 0.077. Add this one, 0.0777, just keeps on going, right? So we're demonstrating that infinite geometric series. So what we can do is we can use our formula. Okay? We can go A is 0.07, R is how can we find R? Sorry. How can we find R? How do we find R on geometric series that we don't know R if we have the sequence? How do we do it? In arithmetic, we can subtract the previous terms. For geometrics and its multiplication, we can what? Divide. Good. So I just want to go this one. Whoa. Did not mean to do that. I want to go this one divided by that one. T2 divided by T1. 0.007 divided by 0.07 gives me I believe it was 9? 0.1, sorry. 0.1. Okay, so my R is 0.1. Now we have everything we need. So the sum of the infinite series is going to be 0.07 over 1 minus 0.1, which is 0.07 over 0.9. And you simplify that, that is going to be 7 over 90. That's the fraction. So if you put 7 over 90 in your calculator, it's 0.07 repeating. So I think that's kind of neat. But I guess I'm a weirdo math guy. Okay. All right, that's it for today. All right, let's get this thing.